everyone. Back to the session of Machine Learning for Cancer Detection, Part 2. We have covered the following points before, that is, foundation, that is, what is cancer, why early detection matters, and quick overviews of three focus cancers, that is, blood cancer, breast cancer, and skin cancer. And then we covered data and pre-processing, in which we covered where our data comes from and how we can clean it. And we covered supervised learning algorithms, and that is where we will go through. We have went through 8 ML algorithms, and now let's continue further. Now we'll be starting with deep learning and cancer specific models. In this part, literally we'll go deeper. Like this is deep learning and cancer specific models, where we will see how convolutional neural networks, that is CNN, power modern image based cancer detection, and how blood, breast, and skin cancer each get their own specialized modeling approach. Yes. Now, deep learning is really neural networks taken further. That is, many more hidden layers stacked together, letting the network automatically learn increasingly abstract features directly from raw data, that is, especially images, without a human manually designing those features. The architecture that dominates medical imaging is the convolutional neural network, or CNN. CNNs are the engine behind most modern image based cancer detection, that is, mammogram analysis, blood smear classification, and skin lesion detection. All typically use some form of CM. In some published studies, deep learning models have matched or even exceeded dermatologist level accuracy on specific skin cancer tasks. When trained on large, high quality, diverse datasets, that's the key requirement compared to classical models. Deep learning needs a lot more labeled data and compute power, usually GPUs, to train effectively. Let's understand it this way, if a classical ML model is like a skilled technician following a checklist you gave them, a deep learning model is more like an apprentice radiologist who has looked at 10,000 scans and started developing their own intuition for what looks off without anyone explicitly telling them the rules. This is what deep learning is. Now let's get specific and look at how these algorithms actually get applied to blood cancer. There are two parallel approaches. The first uses structured lab data models like random forest, XGBoost, or SVM trained directly on CBC values, that is, white blood cell count, hemoglobin, platelet count. The second uses image based models, that is CNN trained on microscopy images of blood smears, learning to visually spot the distorted shapes characteristics of leukemia cells. Increasingly, researchers combine both a hybrid approach, feeding lab values and features into a combined model. The common target categories are acute lymphoblastic leukemia, that is ALL, and acute myeloid leukemia, that is AML, and simply normal cells. It's like diagnosing a car problem two ways. That is, you can check the dashboard readouts. For here, you can say the numbers like CBC values, or pop the hood and visually inspect the engine. Here, it can be images like blood smears. The best mechanics often do both. Yes. Now let's have a look at a dataset I have downloaded from Kaggle for blood cancer. Yes, so there are various images. Let's have a look. we will be using training data. So data is in three folders. We will be using folder 0 dataset. These are ham images. Yes. Now let's get back to our PPT. Breast cancer. For breast cancer, the two-track pattern repeats. On the tabular side, models like logistic regression, SVM, random forest, and XGBoost train on datasets like Wisconsin. That is exactly what we do in our live demo. In previous session, I have shown you the dataset for breast cancer. On the imaging side, CNNs train on mammograms or histopathology slide images to directly detect and classify tumors. A technique that comes up a lot here is transfer learning. That is, instead of training a CNN from scratch, researchers take a model already pre trained on millions of general images like ResNet or VGG and fine tune it on a smaller set of breast cancer images. This works because the model already recognizes general shapes and textures and just needs to adapt to the medical domain. The final output is typically benign or malignant, sometimes with a severity grade. Let's understand it like this, say, um, let's say transfer learning is like hiring someone who already knows how to drive a car and just teaching them your specific delivery route instead of teaching a complete beginner to drive from zero. You are reusing knowledge that already exists. Okay, in this is what like transfer learning is. Now let's see how cancer detection how breast cancer detection model works. I have run it on Colab. So we do have its Jupyter notebook. Yes. So let's go to Colab as it takes time to run. So I have already run, but you can just go through it. Yeah. Yeah. So this is the code on Colab. Here, pip install Q is scikit-learn matplotlib joblib. It installs three libraries in Colab that is quite less console spam. Okay. Then here we import JSON, joblib, and matplotlib. JSON is not actually used in this, but yes, for saving results in the original script, and it is harmless. Okay. And joblib used to save or load the train model to disk as a single file. NumPy is for numerical operations, and matplotlib is for plotting the confusion matrix and ROC curve. Yes, and here this from sklearn.datasets import load breast cancer. It imports the function that loads the built-in Wisconsin breast cancer dataset. So no download is required. I just downloaded it to show you how the dataset looks like. Okay. Now rest. These are all the important algorithms and tools that has to be imported, and we'll be using all this later. And here I have used seven models, that is logistic regression, SVC, that is support vector classifier, decision tree classifier, random forest, and KNN and naive Bayes. So I have used all these algorithms over here, and we have used various evaluation tools such as confusion matrix, then ROC curve, accuracy score, AUC, F1 score, precision score, recall, and all. Okay. Now here random state 42, what does it mean? That is, it is a fixed seed number. Anywhere randomness is involved, that is strain or test split model initialization. Using the same seed means you get the exact same result every time you rerun it. That is critical for reproducible, repeatable. Okay. Now let's load the data. In this line, that is load breast cancer, returns a bundle like object containing everything, that is the raw numbers, the labels, and the column names. Okay. And data.data is a 2D array that has 569 rows, you can see, and 30 columns, that is features, assigned to X, that is by ML convention. Okay. And here you can see data.target. It is a 1D array of 569 labels, each either 0 or 1, where assigned to Y means lowercase, by convention means the answer label. So here you can see out of 569 samples, we have 212 samples as malignant and 357 samples as benign. Here you can see that benign patients are more than malignant. This is also called as imbalanced class. So this concept from your data preprocessing slide. Okay. Now let's come to preprocessing and split them scale. Here, this two statements split the 569 patients into a training set that is used to teach the models and a test set that is held back, used only to check performance on unseen patients. And the test size is zero point 0.2, that is 20% of the patients go to the test set, that is about 114 patients, and 80% about, that is 455 patients, go to the training set. Okay. And random state is equal to random state. It makes the split reproducible, same 20% every run. And stratify equals to y. That means it ensures the malignant test to banning ratio is preserved in both the trained and test set. So the test isn't accidentally all malignant or all malignant by chance. Now here you can see standard scaler creates a scalar object that will rescale every feature to have mean 0 and standard deviation 1. So a feature ranging from 0 to 2000 and a feature ranging from 0 to 1 become comparable. And here you can see dot fit transform X train. Here, two things happen at once. That is, dot fit calculates the mean or standard deviation from the training data only, and then transform applies that scaling to the training data. And you can see scalar dot transform X test. This applies the same scaling learned only from training data to the test set. And critically, we do not call fit again here. If we did, then we would be peeking at the test set statistics, which would leak information and make our evaluation dishonest. This is the no leakage principle. Let's move further. That is feature importance. Here, uh, random forest. Okay. Here it creates a random forest with n estimators equal to 200, meaning 200 individual decision trees inside it. And it trains it. The forest looks at the scale training features and their true labels and learns patterns. And we are calling this one, this what RF probe feature, not the final model, because here it's just being used to investigate which features matter. That is a diagnostic tool, not the final classifier. So, yes, the line top features till you can say score 4F. Yeah, so after training, random forest automatically calculates how much each of the 30 features contributed to reducing prediction error as a byproduct of building all those trees. And here you can see I have used this zip features and top features. Yes, pairs each feature name with its important score and sorts those pairs from highest importance to lowest. And the for loop prints each one formatted with left aligned in a 25 character wide field and four decimal places. Okay, this means core 4.4f, that is four decimal places. Okay, so you can see worst parameter, worst area, worst concave points, mean concave points, worst radius, mean parameter, mean. Each number is that feature's share of the model's total decision making weight. That is, they would sum to 1 across all 30 features, not just these 8. Here, worst parameter is the single most predictive measurement, that is 13.3% of total importance, followed by worst area, and next you can see worst concave points. Now, here you may notice a point that is size related and shape irregularity features dominate, matching the medical intuition from the okay more irregular cells like nuclear signal malignancy. Now, here we are training all 7 models like logistic regression, SVM, decision tree, random forest, k nearest neighbors, name base, and ANL. Okay. ANN is a neural network with where we are using MLP, that is a neural network with two hidden layers. The first with 64 neurons and the second with 32 neurons. Okay. Now, here there are two empty dictionaries to collect results as we go. And the loop goes through each of the 7 models at a time, where dot fit X train Y train that trains that model on the scale training data and asks the trained model to guess a label that is 0 or 1 for every one of the 114 test patients. And then it asks for probabilities instead of hard labels. It returns. So, yes, let's move further. Here we have calculated five matrices by comparing the model's predictions, that is, uh, threads and probes, against the true test labels, that is Y test, and stores them in the results dictionary under that model's name. Here ROC AUC score uses probes, that is probability, and not threads. Okay, because AUC needs to know how confident the model was, not just its final yes or no answer. Yeah, and here fitted model's name equals to model saves the actual trained model object itself and not just its scores. So we can reuse it later, for example, for cross validation or plotting and the final prediction. Okay. Now here, this line prints a formatted header row, then a line of dashes as a visual separator, and then one row per model with matrices as percentage into zero. Okay. Now let's start with logistic regression. It has correctly classified 98.25% of the 114 test patients. And of the patients, it flagged as benign, and 98.61% were truly were. That is precision. Yes. Let's come to now the patients who were truly benign. It correctly caught 98.61% of them, that is recall, and ROC AUC is 0.9954, means it separates the two classes almost perfectly across every possible decision threshold. Now, similarly, we can see for decision tree, SVM is almost, you can see, same. So let's go for decision tree. Decision tree is the clear weakest performer here. As you can see, it has 92.11% of accuracy and 0.9163 AUC. That is exactly matching what we said on slide. And a single tree tends to underperform and ensembles. Next, we can talk about KNN, that has a striking 100% recall, meaning it caught every single actual Benning case in the test set, but its precision is 96%, is a touch lower, meaning it occasionally mislabeled a malignant patient as Benning's opposite. And actually, here means a few malignant cases got called Benning incorrectly and are captured elsewhere. More precisely, some patients it called Benning were actually not, and that's what pulls precision down slightly. Okay, so here you can see best model by ROC-AUC is logistic regression. Okay, we have written this for getting the best name this. Now let's see cross validation. Here, Crosswell score retrains best model, that is logistic regression, five separate times on different train or test splits of the entire data set, that is scalar.transform X. It scales all 569 patients, not just the earlier training set, but each time scoring it by ROC AUC. Here, CV equals to 5 means five-fold. The data gets split into five equal chunks. Each chunk takes a turn being the test and fold, while the other four are used for training. Then, here, CV scores comes back as an array of five AUC scores, one per fold, and dot mean and averages them. Dot std measures how much they vary from each other. Yes. Now let's see the output. The output is five-fold CV ROC for logistic regression, that is 0.9954 plus minus 0.0043. This meaning the average AUC across all five-fold is 0.9954, that is nearly identical to the single split result, and the small plus minus 0.0040 standard deviation tells us the model is consistent. It performs almost the same regardless of exactly which patients ended up in the test code. This is the reassurance cross validation and is meant to give our earlier 0.9954 result wasn't a lucky fluke from one particular split. Yes? Now let's move further. Here, it is we have plotted confusion matrix and a ROC curve. Yes? Now, this statements regenerates predictions and probabilities specifically from the best model, that is logistic regression over here, and on the original test set for plotting. Okay. And this fig axis creates a figure one row, two columns of plots by side, and yes, sized to 12 into 5 inches. We have given here the size. Okay, 12 comma 5. Now here, this line CM equals to confusion matrix Y test spreads test builds the 2 by 2 table of true and false positives, negatives we discussed on confusion matrix slide. Yes, here confusion matrix display draws it as colored grid on the left and subplot using a blue color scale without a separate color bar legend to save space. Okay, you can see this. Here, ROC curve calculates the false positive rate, that is FPR, and true positive rate, that is TPR, at many different probability thresholds. The underscore, see here you can see FPR, TPR, that is false positive rate and true positive rate. Okay, and the underscore throws away a third returned value, that is threshold list itself, which we don't need to plot. Okay. So here, dot plot draws the actual ROC curve as a T line labeled with its AUC score. And this, you can see axis1 dot plot. This one draws a diagonal dashed gray reference line. This represents random guessing, that is AUC equals to zero point 0.5. So students can visually see how far above random the model performs. So this is your AUC equals to 0.5, and this one is your 0.995. Okay. And these are the labels for x-axis and y-axis. In x-axis, we have labeled as false positive, and in y-axis, we have labeled as true positive. And this is our 2 by 2 confusion matrix, where 41 are true positives for malignant. That is, they are correctly caught 41 malignant cases. Then there is one malignant patient wrongly predicted. Yes. And one malignant patient wrongly predicted benign, that is a false negative, the dangerous error type. And we can see this one, That is one benign patient wrongly predicted malignant, a false positive. And here we can see this one, that is 71 correctly identified benign cases. And out of 114 test patients, only two were misclassified total. Here you can see the curve shoots up almost immediately to the top and stays there, meaning at every strict thresholds, the model catches almost all true positives while producing almost zero false positives, and it sits dramatically above the gray diagonal, that is a random guessing line. The legend confirms AUC equals to 0.995 and visually matching the number from block 5's table. Let's move further. Here, joblib.dump serializes, we are saving the model, okay. It serializes, that is, converts to a storable file format, a Python dictionary, bundling three things together, that is, the trained model itself, the fitted scaler that is needed to pre-process any future new patient the same way, and the model's name as a text plate. Okay. This gets returned to a single file, that is breastcancermodel.joblib in Collab's temporary storage. Now here's a question. Why bundle the scalar with the model? Yes, just think of it. Any new patient's raw numbers must go through the exact same scaling transformation before the model can use them. That is, saving them together prevents a mismatch later. Getting? And this output just shows that it's the confirmation that file has successfully saved and written. Now this just takes just the first patient from the text set, and it keeps it as a 2D array with one row, and scikit-learn model expect 2D input even for a single sample. Okay. Now here sample scaled scalar dot transform. It applies the same scaling used during training and never refitting, that is to this one patient's raw measurements. And this line returns an array with one prediction in it and extracts that single value 0 or 1, and here predict that probability line gets the first only patient's probability pair and gets the Benning probability specifically. Here we have used if else. Yes, it converts the numeric code 0 or 1 back into a readable word. That is remembering the encoding from block 2. 1 equals to benign and 0 equals to malignant. Okay. And here we have written probability equals to 0.2%. It formats a decimal like 0.003 as a percentage string like 0.30%. Now, here you can see for this part of code, this one, prediction is malignant, yes, and a banning probability 0.00%. It implies that patient was predicted malignant with essentially 0% chance of banning. Okay, now let's move further. Here, this line implies that it checks if the winning model has learned linear coefficients, that is true for logistic regression and SVM with a linear kernel, and false for tree-based or KNN models. This makes the explanation code safely skip itself if a nonlinear model had one instead. Okay. And here you can see we have written best model.coef 0 sample scale 0. It it means 30 learned weights, one per feature. That is how much each feature pushes toward benign versus malignant in general, and multiplying each weight by the specific patient's scaled feature value gives the feature's actual contribution to this prediction. This is the manual exact as shape for linear models trick discussed. Okay, and here you can see np.add sort. This sorts all 30 contributions by absolute size, that is biggest sample impact cost, regardless of direction, and keeps the top 5 indices. The loop prints each of those 5 features, whether it is push toward banning, that is positive contribution, or malignant, that is negative contribution, and by how much. Okay, so here you can see the output. This is the output for that code. All 5 top contributors push toward malignant, that is all negative numbers, and by fairly larger similar magnitudes, that is minus I guess 1.62 to 2.1, meaning this patient's diagnosis wasn't decided by one dominant feature but by consistent pattern across several tumor size and texture measurements. Yes, which is exactly the kind of show your work explanation. Yes, now let's move back to our slide. Now let's move further. Skin cancer detection. Skin cancer detection is almost exclusively CNN based since diagnosis is fundamentally visual. Models train on large collections of dermoscopic images to classify a lesion as, say, melanoma versus a benign mole. The two data sets you will see constantly here are ISIC and HAM 10,000, which contains around 10,000 labeled dermoscopic images. Transfer learning is heavily used here too. Architectures like ResNet, EfficientNet, or Inception, retrained on general images, get fine tuned specifically on skin lesion data because skin appears differently across skin tones and lighting conditions. Data augmentation becomes especially important. That is, rotating, zooming, and color adjusting training images to help the model generalize across a diverse patient population. Let's say it's like training someone to spot counterfeit money. If if you only ever show them examples under one lighting condition, they'll struggle under different lighting augmentation. Yes, and it's deliberately practicing under many conditions, so the skill actually generalizes. Yeah, let's move further. Sorry. Now, image based cancer analysis. Let's talk about how a computer actually sees a medical image because it's genuinely different from how we see it. To a computer, an image is just a grid of numbers. Yes, there is a pixel array with no inherent concept of suspicious dark spot. The model has to learn that pattern purely from numbers. CNNs shine here. Yes, they automatically learn a hierarchy of features. In the earliest layers, the network learns simple things like edges and textures, And in deeper layers, it combines those into more complex shapes. That is, and by the final layers, it might recognize something as specific as the irregular border pattern typical of malignant lesions. Before any of that, images go through pre-processing, that is resizing, normalizing pixel values, adjusting contrast, and reducing noise to compare images on a level footing. Yes, here it's like teaching someone to recognize a face by first learning edges and curves and then eyes and nose made of those edges and only then whole faces made of those features. Each layer builds on the last. Here you can take an example of teachable machine. Yes. Yes, so Teachable Machine is a free web based tool by Google that allows students to train machine learning models using their own images, sounds, and body poses, all without any coding. Yes, it is an excellent visual way to introduce artificial intelligence. Okay, so what are the like steps that how teachable machine works? Let's see. First, it gathers the data, that is, it creates classes and feeds the computer examples using a webcam, microphone, or uploaded files. And then it trains the model. There's a click button, click the train button, and then the computer instantly analyzes the data to learn the pattern in your examples and then try out the model live to see if it currently correctly guesses the new inputs, and then you can export the model for use in websites, apps, or coding platforms like Scratch. And you can build various projects like image project that teaches the computer to recognize objects, facial expressions, or hand gestures using a webcam, or it can be an audio project where it trains the model to listen for specific sounds using the microphone, example clapping, whistling, or spoken keywords. Or it can be a pose project that it uses the webcam to track body movements, recognizing different yoga poses or sitting or standing or something. Okay, so let's move further. Histopathology and medical imaging. Histopathology is the study of tissue under a microscope, and it remains the gold standard for confirming a cancer diagnosis. That is, even if imaging or blood test raise suspicion, a definitive diagnosis usually still requires a pathologist examining tissue from a biopsy. Yes, the modern shift is toward whole slide imaging or WSI, where tissue slides are digitized into extremely high resolution images, that is gigapixel scale, larger than thousands of regular photos combined. ML models can scan these digital slides and assist pathologists by flagging cancerous regions, counting mitotic figures, that is, cells actively dividing, and indicating tumor aggressiveness, and providing a consistency check on grading. The challenges are like these images are enormous and staining varies between labs, and building reliable training data requires expensive export verified labs. Yes, let's have an example. Um, imagine imagine like proofreading a book the size of a football field printed in the tiny text where different pages were printed with slightly different ink shades, and that's the scale challenge a pathologist or an AI model faces with whole slide imaging. Yes. So for today, let's stop here. In next session, we will be starting with the demo on blood cancer. Like we will be seeing how it can be run on Colab, and then we will further see evaluation and explainability. Yes. Till then, you can just go through what we have studied today. So thank you. And if you have any queries, so you can reach out us at biotechrebion@gmail.com. Thank you.